I just wanted to take a few minutes to talk to you about basin filling, set the stage as much as anything for the role of basin filling in geothermal fluid flow. And mostly I want to concentrate on a couple of points. I want to concentrate on a couple of points that I'll kind of bring up along the way about basin filling. But, excuse me, probably the most significant thing to take from this morning's session is just that when we make it is that these sedimentary basins are going to be some kind of a tectonically generated basin, which we fill up with sediment. And the way that we fill that with sediment is going to dictate the fundamental first-order plumbing of the entire system. So the more we can understand about how the basin actually gets filled and the processes that are entailed in that, the better we can actually predict and make decisions as far as what could be potential flow paths. So I'm going to address some of the basic science of that. I'm going to begin by just, whoops, that's working. There we go. That jumped too far. Begin by just talking about some of the basics, because I know that we've got a wide variety of people in the room. See the slides okay?
Yeah.
Can you dim them? No? All right, that's fine.
Turning off the lights helps a lot.
Turn off the lights. It's cool. Yeah. All right. So to begin with, I know that one of the beauties of putting together this particular Penrose and this particular subject in general is there's a lot of different people with a lot of little different parts of the puzzle that are all involved in this from a lot of different walks of life and a lot of different research interests. And in that, so let me begin by just kind of covering some of the basic points, and I'll move on to some of the specifics. First off, the idea that you would have sedimentary basin geothermal is pretty simple. You drill a hole, and you in one place, and you drill a hole in another, and you suck water out of it, and the circulation path sets up, and before you know it, you've got geothermal power. Of course, the issue becomes what's the plumbing down in this area, and what are the paths by which water moves from one hole to the other. Simple enough. Stratigraphy can't be that complicated. It looks a pretty layer cake when you look at it, and it looks pretty simple, and the idea should be fairly simple. You drill down to the unit you want in one well, and you drill down to the unit you want in the other, and then turn on the pumps. The reality of sedimentary units is a little bit different. So when we go out and we look at sedimentary units, this is what we usually see. We see complexly intertwined bodies of sediment that come and go, and we see them connected by thinner units. And we find ourselves constantly asking these questions. Oops, I wasn't supposed to push that button. We constantly find ourselves asking these fundamental questions as to whether reservoir or porosity or flow units that we've tapped here, are they actually connected to the adjacent one like this, or are they actually isolated like that? So, of course, it's a bummer if you drill your well here expecting to pump out there, and then you find out you got this situation instead of that one. But this is the reality of actually doing subsurface work. The stratigraphy is often quite complicated and doesn't do what we expect. And when we look at one of these situations like this with the little units that are coming and going and connecting, we look at it from the top, it kind of looks like that. So this is a actual map of the Rhine-Meuse river system over the course of the Holocene, and all these little colored lines are little channel belts and so forth that would theoretically be flow paths. So the plumbing is quite complicated, as you can imagine. If you're working from the surface and try to drill a hole in one of these spots and hit one of these, there's no guarantee that the next one you hit would connect up with it. You would actually get a through-going flow path. This thing is not behaving. Well, gee. Oh, yeah, there's something going on here.
It's that hot music.
Okay. There we go. Got it. Yeah. It hadn't. The challenges. First off, part of the challenges that we're facing when we're looking at sedimentary units is that within the sedimentary units that we thought were fairly uniform, you look inside and there's lots of little heterogeneous, little clay layers and so forth scattered around that actually baffle and direct the flow in directions that we don't particularly like. Probably the bigger issue probably the bigger issue is that when we start trying to draw up units, when we start trying to draw up units and start drawing out the plumbing, we find that things that we thought should connect don't. Things that shouldn't connect do. So designing out a flow, so looking at a cross-sectional area where we put injector and extraction wells and then actually start asking what connects up and what flow paths will connect up, we end up hitting things that connect up, that don't connect up, like the pink, and things that do connect up, like the brown. And like I say, knowing which ones are which is part of the key to the battle. Okay, so all of that means that when you start actually putting in an injector and an extraction well, you always end up with the same question. Hold still, this thing has actually got a flaw. Okay, there we go. When you actually put in an injector and an extraction well, you always end up with the same situation. You put a well in and you start pumping in water and you ask, where'd my water go? Because you have multiple different flow paths in multiple different directions in complex units that can put your flow going any number of different ways that you weren't particularly expecting. Okay, so a primer on looking at sedimentary basins and what we do. First off, on the simple point of view, we have plate tectonics, which generates various subsidence trends. We get different kinds of basins. Common basins would be a rift basin like this by tension, or a foreland basin that you might generate by compression, and you'll generate topographic loads which fill up with sediment. And you end up with the sediment coming into these basins as they sink, and you'll create a complex internal stratigraphy in these basins that record the processes at hand of deposition as the basin is subsiding. And the reflection of the rate at which sediment is, what you get in here is going to be a reflection of the rate at which sediment is coming in versus the rate at which we're generating space to store it. We have lots of different ways that we've been attacking this over the years. Sequence stratigraphy is a favorite one. We'll come in here and look for common stratigraphic horizons that will reflect events and at least allow us to sandwich our units into stratigraphic layerings that record, at least allow us to sandwich our units into stratigraphic layerings that record specific units, that record specific events, that have some commonality that allow us to break out potential flow paths. And of course, the oil industry has been using this for ages. It's not particularly exact, but it is better than nothing for sure. When we look at a basin at the scale where we're talking about individual flow pipes, where you're talking about an individual permeable body, and we're trying to connect up with it on either end, then we start actually addressing that from the point of view of the depositional system. So the way that we get at basin filling processes typically is we will look at a depositional environment like the Mississippi Delta, and we'll look at all the different loads, and we'll look at the parts, and we'll look at the processes that are taking place, the processes of deposition that are generating sediments. We'll look at the sediments that they generate. And from these characterizations, we'll make some kind of a depositional model, some sort of an idea of how these systems generally produce flow units. So you can see these little bar finger sands are nice little flow units you might get in a Mississippi Birdfoot type delta, and they're generally encased in less permeable mud. So these would be our pipes in general, and that's sort of a model. When you actually look at them in rock, however, you end up seeing something that looks kind of different. So typically, we follow this kind of a trajectory. Depositional environment to depositional model, to actual rock, to actual predictions of what would be in the rock. So this is a deltaic deposit in the book cliffs of Utah. Okay, from there, our understanding of those depositional environments allows us to get at detail about what the depositional units would, how the depositional units look. So these are a couple point bars that are stacked up in the Belly River deposit. As you can see, they have some pretty complex internal stratigraphy. And from that, you can start making flow models that would predict what the permeability distribution would be. And from those, start making flow models from injector to extraction. So this is typically how we'll approach these sorts of things. Look at the data we have, make predictive models about what we can't see, and then devise a flow model that would actually work in that type of system. Okay, so that's the simple gist of how we go about doing what we do and how we get at the principles of basin plumbing. We start from the basic science of what's the tectonic and the sedimentary regime, and then we work our way up to the specifics of the depositional environment and depositional system to try to get at predictions of what would be the flow paths and the different permeable and non-permeable units you might lay down in a given deposit in a given system, match the data with the model, and try to use that to develop the best possible flow model. And that's what we go with. From all of that, though, there's still some very vexing questions, some large uncertainties that we're dealing with. There's plenty of them to play with. I'm just going to point out a couple here that tend to be things that we're thinking about quite a lot these days. One of them is, the idea is simple enough. You have a basin that's being formed by tectonics. You have this half robin here. You have a down drop block here. You're dropping the basin. You're creating an accommodation area for sediment to accumulate. You're generating sediment in the hinterland that's pumping into it. So you've got a QFS. You've got a discharge of sediment coming into this basin from the hinterland, filling the basin, and how much sediment is coming in at a time will determine whether you'll completely fill it up, or whether you'll overfill it and get bypass out of it, or you'll barely fill it, or whether you'll actually underfill it. Likewise, the kind of sediment that's coming in and the amount of it you're getting in different grain size will tell you a lot about what kind of plumbing pattern you could get. So on first order, the nature of the sediment supply versus the subsidence is a real control on what the deposition is going to be. So we've worked with tectonics a bit, and I'm going to leave it to Teresa to talk a little bit more about the tectonic aspects of it. But that said, at this point, one of the big things that we're left with is this question: how do we actually get at these ancient sediment budgets and translate these to the actual plumbing pattern? So particularly the tectonic variable in subsidence is bad enough. But we've got ways to kind of backstrip and back calculate some gross numbers on that. But getting at how much sediment is coming into the basin, this is a dark world. We really have very little to go on in terms of actually getting at real sediment mass balance budgets when we're filling up a basin. A couple approaches that we take. One of them is the fulcrum approach. I didn't print, so this is mine in press. But this idea says we got a drainage, we got a basin out in here, and somewhere in there you're taking a cross section. You're looking at the sizes of the channels, and you're looking at the grain characteristics, and you're trying to inverse model the entire sediment transport regime to try to get at some idea of the size amount of sediment these rivers would carry as a measure of what's coming to the catchment, but also what's clearing this area and going on out into the basin. So that's one approach. Another approach is to go straight for catchment modeling, reconstruct the catchment area, and start doing models of rainfall and critical bed shear stress and various parameters about a basin that we presently use to try to figure out how much sediment a basin delivers and try to apply it in the ancient. As you can imagine, when we start getting into the rock record and we don't actually have these basins on the surface anymore and we don't have the actual rainfall that they have, we're making a lot of guesses when we do that. So this is an area that's very pioneering, and getting at proxies allows to constrain some of these variables that we have in the modern that we don't have in the ancient, is an area where we're just really getting some ground. Even so, catchment modeling, pouring in the sediment, it dictates something about what kind of basin deposits that you're making and the grain size variation. Even with that, set supply to plumbing architecture, we're completely lost on this one. In terms of actually making predictive models about what kinds of sediment we're delivering in the basin and how that's going to translate into individual plumbing pathways, we're still doing a lot of work on that. So these are areas that are basic science areas in sedimentology where we've gained a little ground. We need to gain some more ground, because ultimately, if we're going to be able to walk into a basin and make some predictions and say, this is what you should find and this is where it should be, then these are questions we have to answer. Another vexing question becomes at the next level down, at the level of the plumbing. This idea of let's take the depositional environment, make a depositional model, and translate it into the rocks is a good one, but when we actually look, you find that there's a lot of questions about how you get from here to there. These don't look particularly like those. So this would be what you would predict as your sandy conduit here, but that's a real sandy conduit in the rock record. So when we actually look at what we see in the rocks versus the nature and the geometries and the system that made it, we got a little bit of a mismatch and a lot of things in between we're trying to figure out. So what actually is being preserved in the rock is a fundamental question we're after. And to get at this and show you some of the issues with that, consider this. This is just a series of ripples. A small ripple migrating distance, their own wavelength. So about every hour you'll migrate a little bit. They'll migrate a wavelength and they'll pile up about 5 centimeters of sand. So what that means is over time that if you actually did this continuously, you come up with a rate that's about 100. You come up with a rate that's about 100 kilometers per 1,000 years of deposition. So that would mean, let's see, we're only 68,000 kilometers for the entire radius of the Earth, so, and we're a little older than that. So clearly, we have some issues in terms of how much of the actual processes in the model we're actually preserving. So questions about the fractal relationship, about the amount of gap in the rock record and the amount of noise in the stratigraphic record made some people question whether we preserve depositional patterns at all in the rock record, but yet there's some geophysics, there's some modern era photos, clearly we do. So it clearly happens that modern depositional systems make patterns like this braided river that we actually do see in the rocks. The way that we're going to preserve rocks then, at least here's the thought on how this works, is that we preserve in snapshots. Essentially, you're not preserving that whole series. You're preserving one little snippet, one little quick snapshot of what happened in the past, and you're preserving it at different hierarchical levels. So the ripples here, a bunch of collections of ripples make a snapshot of a bar, and a bunch of snapshots of bars make a channel fill, and then eventually you work yourself up to a basin fill. So what you end up with when you look at the actual sediments is fragments of stuff. You don't end up with a whole body, you end up with a little piece. Like that one little piece of a bar is preserving over what was once a whole piece of the Lena. This particular braided river of the Mississippi preserves intact simply because it's a glacial outwash event. It came, it went, it was done, it froze. But it's only one of all the things that have one channel of all the ones that existed during the Pleistocene. But that said, when we work with snapshots, we're used to that. So when we go collect a bunch of snapshots, we'll go and say, hey, we got some snapshots. Some of them, you could have shot that picture anywhere. And you go, where the heck did I take that? But others, you'll look at them and go, I have a pretty good idea where I took that. That was someplace in the Middle East. And then you'll get some that are excellent indicators. You'll have a handful of snapshots that'll tell you exactly where you were and exactly what you were doing. And you realize, I should stop going to countries before they collapse. But anyway, so the thing is that you end up with situations where when we look in the rock record, this is the way we usually handle it. We look for indicators. Of all the snapshots that we got, we look for the snapshots that are very telling. Thing is about these snapshots is a collection of small snapshots collecting up make bigger snapshots. So smaller snapshots of all these little deposits, of all these little bars, and all these little dunes and so forth, end up collectively making a snapshots of larger bar features, which collectively make snapshots of larger channel features. And when you actually break them down, what that shows you is depending on how tightly you want to break down your bodies, you end up with snapshots of various different scales with lots and lots of gaps in between them. So ultimately, the real trick is the rock record is more gap than record. And so we end up with lots and lots and lots of gaps that we end up with little pieces, little fragments of things preserved. If we want to see something different happen, we just change the nature of the set of snapshots. Snapshot preserves something else, we end up with something else. So, if we want to, so in this particular case, there's the Mississippi River, it's a braided river system. We change the nature of the depositional system enough, and in other words, we end the glaciations and we go to a rainfall drain regime, and we go from meandering to braided. So the fundamental pattern of the river system has changed. We just changed the snapshots that we're taking, and we changed some part of the sampling enough to where we shifted it to where now we're recording something, a plumbing system is entirely different. Okay, so essentially what you're doing is many complex interacting fragments of pipes is what you're actually getting. So when you look at a mess like this, and you look at a thing like this, what you have is you had a lot of things that were probably continuous depositional systems, made continuous pipes, that have since been fragmented, and incised into each other to make a very complex network. So that's usually what we're up against. Trying to model something that's taking all these little broken puzzle pieces and putting them together into something that's complex, continuous flow unit is part of the challenge of what we're dealing with sedimentology. We've been doing it for ages. It's not like we can't do it. It's just the more we research it, the better we understand it, the less uncertainty we have when we try to do it. And part of the trick is it's been okay for oil because you could miss a few times. And it's been okay because you weren't necessarily trying to get flow to go over such long distances and such large amounts. So essentially what it amounts to is we're in a position where we just have to up our game. We need to get better at this so that the uncertainty drops. And ultimately it all comes down to the same thing. We have subsurface data, we collect subsurface data, and we're asking ourselves, what is our subsurface data actually trying to tell us about reconstructing the flow paths? So I'll leave it with my little summary slide. So the real big question is, what is our subsurface data trying to tell us? And we already know basin filling makes for some very complex plumbing. Ways to improve that is trying to get at the actual numbers that go into the basin to begin with, and trying to understand a little better what's actually being preserved in the water. Okay, and I'm done. Thank you. Yeah.
I'm going to play devil's advocate here, even though this is stimulating the debate.
Good.
This is crucial for oil, obviously.
Right.
There's a chemical located at a certain position, you got to bring it over. What about the case where it's heat that's located everywhere, and you don't really care what the flow paths are as long as it's connected?
Well, and you know, you've got a point. The thing is that heat isn't really so much the issue. It's there. So we know we've got a heat that's sort of spread. There's slight differences in conductivity, and so there's going to be a certain mosaic of the heat. But ultimately, the heat is there. So the trick is really about getting the water to flow. So yeah, I mean, at some point, you don't care whether it flowed through this individual channel or it flowed through this little piece of a channel, caught that little piece, went through that little piece, as long as it gets from there to there. I think the real trick gets back to something that Kate and Rick brought up yesterday. It's about the nature of the heat sweep. Because in this kind of a complex mishmash, what the problem is you have lots and lots and lots of anitrospacity, and you end up with, what you don't want is breakthrough paths that are quick routes that don't drain. Yeah.
When did you hear about groundwater?
When did you hear about a groundwater hydrology extraction that worried about this kind of stuff?
Well, you don't hear a lot about it. Well, actually, I should say I'm working on a Superfund case right now, and believe me, there's another person on the other side, and we're having great debate, because when it comes to contaminants, they worry about it a lot. But, you know, part of the trick of it is with actual groundwater flow, is that when you're dealing with those, first off, you're often, well, there's 2 or 3 different things going on. One is you have a lot more control over where you drill the hole. Most of the large municipal wells that they'll drill that are meant to extract large amounts of water, they're usually tapping something closer to the surface where they've got a lot more control on what they're actually in. So part of our trick is that the further you go down, the lower the resolution of your seismic, the lower resolution of your data, and the more you're having to guesswork. And so a lot of the things that we're working with have poor resolution. If you could see it, it wouldn't matter. If you could actually see, there's that flow path, I can track it through, no big deal. But like I say, we're dealing with situations where we're down at depths even beyond what the oil people typically are dealing with, and just our resolution is poor. So well, let's put it this way, if it wasn't for poor resolution, I'd probably be out of a job.
But John, the way I understood yesterday is that at the beginning of time, when all the water is at the same temperature, it's not a problem. But once you start circulating, residence time in order to heat that water to the appropriate temperature is crucial. And so, based on what you just said, when you have channels, when you have potential for bypass, understanding where this water flow in order to maximize the residence time is actually quite important.
Yeah, and I would think that would be true, particularly if you start talking about flow convections, and you start talking about replacing the water, trying to get what water's replacing the water that you're actually pulling out. Again, it's one of those things where the more margin for error that you have, the less these specifics become important. And I think what's been part of the case with a lot of petroleum, the analogy in the petroleum industry is what they call water breakthrough. where they worry a lot about where they'll drill the hole and they'll start pulling out the petroleum, and they'll actually get one of these nasty little pipes over here that's leading straight to the water, and so once they suck the petroleum out, it makes a flow path to one of these conduits that's bringing up what would be like lower convecting water in our case. But in their case, it's just fresh water. They don't want it. They're trying to get the petroleum, and they get breakthrough. And it's one of the big threats. Huge amounts of time spent worrying about, will that break through? Will that break through? Will that break through? Trying to understand these complex conduits. But in a broader context, those same kinds of issues about conduits that connect up from greater depths say a lot about what kind of convection that you might actually be able to generate and what kinds of deeper waters you can pull in.
Look, you painted a picture of maximal heterogeneity in the systems you're looking at. Are there intrinsically homogeneous, monolithic reservoirs, aquifers that come out of particular deposition environments?
Repeat the question.
Yeah, is it, the example, what I've been talking about quite a bit is very heterogeneous environments that make a lot of anitrospacy in the system. Derek is asking, are there systems that really don't have that kind of anitrospacy and that they really don't have these sorts of issues? And the answer is, it really all a matter of how much heterogeneity you're willing to tolerate. So an aeolian sand, for instance, is notoriously low in heterogeneity. It looks like a big tank. But on the other hand, it does have some fairly significant baffles in it that represent periods between dew migration. It has pretty significant changes in grain size across the slip faces. Even the most homogeneously appearing units that we see, typically there's tons of heterogeneity in there. It just isn't quite as profound. If it's below your tolerance level, no big deal. But that said, picture yourself drilling a hole in a big aeolian sand drill hole here. It looks like it's some big uniform body of sand where there should be an even sweep between them. But right through the middle of it, there's this little windblown armored lag line right along the path. You pump water here, it's going to go straight through that, an order of magnitude faster than it's going to go through the rest of the fine-grained sand. And, again, you still end up with breakthrough problems.
Yeah, well, I think that's an interesting question, because then the question becomes as to whether you're worse off having baffles that slow down your overall flow rate, which is bad, but having short-circuiting conduits that speed up your rate that might give you short-circuit.
And and I think that's a very valid point. And it's one that definitely was worth some thought. Is that are you better with the radiator model where you're forcing the water to go through lots of constrictions and over lots of contorted paths to get there, versus the ones where it looks like it's just going to be an easy drill here, simple path? Because part of what we heard, yesterday, and what comes out of a lot of these discussions is that if you want to maximize heat sweep, you really want a more complex, contorted, multi-directional path from A to B.
Let's see.
Go ahead. I'm going to Lads it.
Okay, you addressed sedimentation and filling of the basins. Of course, basins can be uplifted and lots of stuff eroded. The complex history can also change the flow possibilities. But this is not my point. Traditional hydrogeologists say, okay, water flows along permeable strata. But there is no school of the gravity-driven flow. People who say the surface topography, and especially the water table topography, dictates where the natural water flow goes. It can go in a cross-formational way.
Yeah, and of course, never underestimate the power of gradient. The fact is that when you set up an injector in a pumping system, it's the same trick as with groundwater. You're creating an artificial potential variability. So I think that's always worked in our favor. Is that that the flow's going to want to go to that direction. Part of the trick ends up being one of, I think, where the flow, if the flow, you're producing enough water and you're getting rid of enough water, I'm not sure how important it immediately becomes that you're replacing and extracting the same water. And so you create a gradient, you draw water to the well, you pull it out, you harvest the heat, you pump it back in. If it's working, it's working. But I think part of the thing there with what you're saying then is just, like I say, a lot of these questions become down to the matter, if it's working, it's working. You know, I mean, people drilled for oil for ages where they just went out and said, I found a seep, I drilled a hole, and they never asked the geologist about it. And it worked. And where it became an issue is when you really had to know a bit more about where the flows were going, where the oil was coming from. You actually had to know these things. At this point, if it's just a gradient is working, then you're fine. That's one reason why groundwater, what's been an interesting study is working in both environmental and petroleum worlds, and of course with geothermal, you see an evolution of technology, because what I notice as much as anything is in groundwater, their immediate problems have not been as intense at first. So they worked with what they call the equivalent homogeneous media, where they'd take extremely complicated heterolithic bodies and they would boil them down to a homogeneous media and model the flow through that, and it worked because what they were asking wasn't that complicated. But once you start getting into deeper and deeper problems, and you're worried about low, water resources on a tighter level, you're worried about salt intrusion, you're worried about contaminant migration. You watched them slowly pick up the technology that the oil companies had been developing. Even now, I mean, I watched the evolution of slim hole geophysical technology. You couldn't buy a geophysical sonde that we used in the oil industry back in the 80s, but now you can buy one, and they'll simply because that technology has worked its way in as their problems have gotten more intense. So I think what the real trick is with geothermal is a fairly simple one. A lot of the technologies that we do in sedimentology and stratigraphy, we've been working on these for a while. The drivers have largely been the oil industry. The water world has been catching up behind it as they've come to the same level of problem and have needed it. And at this point where we're at now, I think with geothermals, the risk factor is just so high in drilling expensive wells that your tolerance for making a mistake and your need to know is just that much higher. So it's really pushing us to actually be able to do a better job of being able to make these predictions.
Thank you, John.
All right, Joe.